Okay. First of all, I wish to acknowledge the organizing committee for inviting me to deliver this keynote lecture. Also on behalf of my co-authors, which are shown here, Dr. De Silva, Professor Parisi, who's a professor of structural engineering, and Dr. Piro, who made most of the dirty work of the analysis I'm going to show you in a while. Few words for the motivation of this research, because observation after most recent earthquakes and even oldest one in Mediterranean area, especially in the most hazardous countries such as Italy, Balkanian Peninsula, including Greece and Turkey, shows that most of the damage suffered by centers is due to the high seismic vulnerability of existing buildings, most part of which are made with unreinforced masonry. And like these representative pictures show, a significant amount of damage is due to local out-of-plane collapse mechanisms. And therefore, our objectives were being the soil foundation structure interaction typically overlooked for such a kind of buildings characterized by shallow foundations. There can be a chance of considering this mechanism for a more reliable assessment of the performance of such kind of buildings in terms of two main aspects. The first one is how to cope with the methods referring, for instance, to response spectra for pseudodynamic analysis, which assume that the structure can be approximated with a single degree of freedom system, accounting for the complexity of the masonry buildings, which makes it hard to approximate them with a single degree of freedom system. And moreover, how can we estimate the effects of soil structure interaction in the increase of the fundamental period of such systems, which can help for a more reliable assessment of the seismic inertial load acting on them, which can be either detrimental or beneficial depending on the part of the spectrum the period fall on. So our first objective was find some simplified method to predict the variation of fundamental period for compliant-based models with respect to the fixed-based conventional models. The other aspect we tried to investigate was to try defining seismic fragility curves, accounting for site amplification and soil structure interaction, and expressing the probability of attaining a given threshold damage level at the increasing intensity measure of the reference input motion, which have to be defined and optimized in order to get a reliable prediction of the expected damage by knowing synthetic parameter representing ground motion. And of course, in this case, in both cases, we not only developed our procedures, but also we tried to test them on well-documented case studies. So for each one of the aspects, I will try to resume the procedure we developed and to show you the assessment on the case study, which are shown in these pictures. Okay, so first step was let's try to represent a cross-section of a masonry building, which is very complex due to the distributed mass and stiffness in the structural elements, due to the embedment of the foundation, due to the presence of intermediate walls and layered soil as a foundation soil. So the first, say, challenge was to find some equivalence criteria to approximate this building as a compliant-based single degree of freedom system characterized by lumped structural parameters and impedance components, frequency-dependent functions, which represent both swaying and rocking foundation subsoil compliance, and thereafter to transform it in a replacement oscillator, which is that characterized by the fixed base and modified values of the lumped parameters, and characterized by frequency, which is typically lower than the fixed base value. Here I'm showing you the well-known formula suggested by Valerio Semic about 50 years ago, which requires a kind of iterative procedure to find out the frequency reduction ratio. And an alternative procedure is suggested by the same authors, is that to refer to quite simplified charts where for a given structural slenderness ratio given by the ratio between the height and the width of the structure, it is possible to predict the frequency reduction ratio by simply knowing soil structure stiffness ratio, which is defined by the ratio between the shear wave velocity, which is for the simplified approach assumed that pertaining to a homogeneous soil model, and the fixed base frequency and the height of the equivalent mass of the structure. So we try to calibrate this method by means of parametric analysis. And here you can see two typical examples of building a foundation subsoil models, with the building represented by load-bearing walls with the thickness decreasing with the height. The soil profile was first assumed as homogeneous by characterizing it by means of shear wave velocity pertaining to the widespread ground type classification criteria suggested by international codes. We, for the softest soil model, also try to assess the influence of heterogeneity in terms of variability of shear wave velocity with depth. And then we consider also further layered the soil model to approximate actual conditions of soil heterogeneity. And for the nonlinear analysis we adopted for the assessment of the fragility curves, we assumed a hysteretic plastic behavior for the soils with the assumption of standard curves for defining the variation of normalized shear modulus and damping ratio with the shear strain. With reference to the material assumed for the masonry buildings, we selected three kinds of masonry types, which are the most widespread in Italy and also, I guess, in the other Mediterranean countries, characterized by reliable parameters representing their stiffness and strength as measured on load-bearing wall panels in the laboratories or suggested by the technical codes. So here in this table, you can see the combination between all the structural slenderness ratios, H over B, the type of masonry material, tough stone, rubble stone, and clay brick masonries, and the soil models we adopted for the analysis. Not all the combination were used for linear and nonlinear analysis, but they were enough to try to assess our method on the case studies I mentioned before. So I can first show you the typical results of viscoelastic analysis. Linear viscoelastic analysis were used for a kind of a dynamic and identification of the frequency response of the building foundation soil models. Here you can see the typical mesh we adopted for flat two-dimensional analysis. This example is relevant to a tough stone masonry with rather squat shape ratio. And in this analysis, being the model linear, we just considered white noise as an input motion applied at the base of the soil model in terms of shear stress history. And we monitored the response of the building and the soil by simply assuming the 3 control points located on the different structural elevation and at the ground level. So here you can see 4 different examples of the time histories of the control points corresponding to as many soil models from the top to the bottom. Here you can see the results of an analysis relevant to rigid soil conditions, which correspond to the fixed base hypothesis for the structure, stiff soil B profile, soft soil C, and very soft soil. So these plots on the right represent the normalized Fourier transform of the free vibration, which easily help to identify the fundamental frequency of the systems. Please note that the soil free field frequencies computed analytically are in most cases reflected by the secondary peaks of the Fourier transform, whereas the main peaks that you observe here are those of the structure with the rigid base in the first case and compliant base with the increasing deformability of the soil. And you can see that although the variation is not as significant as that of the free field soil behavior, the decrease is anyway about, it is not negligible at all, which means that the soil structure interaction is significant for this kind of model. With the use of the results of the numerical analysis, we recalibrate the replacement oscillator model in that starting from kind of structural and subsoil model characterized by a limited number of parameters listed in this left part of the slide, we could calibrate some kind of weighting coefficients which can help in defining weighted average of shear stiffness and inertia mass of all the materials involved in the volume significantly interested by the inertial soil structure interaction mechanism, which consists of the embedded foundation, which typically has the same properties as the load-bearing walls, and the soft soil cover and the underlying stiffer soil for the case of layered soil, or in any case, even in presence of more than 2 layers, we can extend this procedure to obtain the weighted average of stiffness and equivalent stiffness and mass density. With those parameters, we could define the equivalent shear wave velocity, which can be substituted in the conventional expression of the stiffness ratio suggested first by Velezzo and Meek, in order to use the same kind of charts with obtaining a prediction of the frequency reduction ratio and therefore of the period increase ratio, which is different from that obtained by the oversimplified hypothesis of a homogeneous subsoil model. So we try to assess these procedures, this procedure on a case study, which is the subsoil and building stock of the historical center of a very nice city in southern Italy, which is well known worldwide for its particular environmental heritage, characterized by the existence of a number of anthropic cavities dug in a soft calcarenite formation. But our interest was not in that area, but on the most inhabited area, which is built on the, say, on the ridge of the Sassi areas. And it is characterized by a high number of masonry buildings. In this area, thanks to cooperation of researchers of the National Research Council, we could rely on the availability of a number of reliable investigation in terms of borehole logs and geophysical tests. We also performed our own downhole test and also electric resistivity tomography, but especially the availability of a high number of experimental measurements of soil foundation structure frequencies taken on buildings and processed in terms of horizontal to vertical spectral ratio. So we selected a representative sample of 9 reinforced masonry buildings. All of them were founded on the formable clay layer lying on the calcarenite soft bedrock with variability of clay thickness, which overall increases by going away from the Sassi area. And for some of the buildings which were investigated by the National Research Council, founded on directly on the calcarenite formation, we had the measurement of the natural frequency, of course, by horizontal to vertical spectral ratio, and by fitting this measurement, these measurements of the experimental frequencies against the height of the building, we could get a relationship which for us represents the reference estimate of the fixed base frequency of the building with a given height. Whereas if you plot the, while plotting the frequencies, experimental frequencies of the building founded on the clay, the frequency resulted significantly lower, and they are as much lower than the fixed base values as the thickness of the clay formation increases. So here you can see a set of pictures of the set of buildings we adopted, at least in this study, to assess our procedure. You can see here a set of 4 very similar buildings with the same shape ratio, which is quite low, and a moderate increase of the clay thickness of the layer. And for them, even with this relatively low variability of subsoil condition, still a non-negligible reduction of the frequencies observed. In this second set of 5 buildings, which are characterized by instead by quite different shape ratios and subsoil conditions overall, featured by higher thickness of the clay foundation layer, the measured frequencies are significantly lower than those of the previous set. Here you can see summarized the cross-section of the building subsoil model for the first set. You can see the clay thickness increasing from 0 to no more than 5 meters. And we called this set of buildings squat thin because the squat shape of a building and the thin clay layer thickness. And for them, the comparison between the experimental frequency, the ratio between the experimental frequency and the assumed the fixed base frequency yields a value not very lower than unity. Instead, for the other set of buildings, which are on the average more slender than the others and characterized by higher thickness of the clay subsoil layer, the frequency reduction ratio appear on the average lower. So we compare in this plot the experimental frequency with respect to that predictable by the traditional approach by Valesius and Meek, and you can see that first the experimental frequency lie well below the fixed base value corresponding by their building height, which is of the order of 7 Hertz, and also that the traditional approach under predicts the frequency of the soil foundation structure system. Instead, our method in some way can catch the right variation of the frequency because it yields frequencies, analytical frequencies much closer to the experimental values. Second part of the study was to analyze the effect of soil structure interaction on a linear dynamic response and fragility of soil foundation structure system. This time, we consider a nonlinear behavior for both soil and structure, and also we consider actual seismic records as reference input motions. From the analysis, we monitored the soil and foundation and structure response by higher number of control points and kinematic and dynamic quantities. Here you can see the set of response spectra of the reference input motions. The selection was made based on the method called the cloud method in the literature, which make use of a high or seismic signal characterized by high variability of both amplitudes and frequency content, which helps us with the relatively limited number of dynamic analysis to define the log-log relationship between a selected engineering demand parameter representing the performance of either the structure of the foundation or the soil and a selected intensity measure of the reference input motion. By means of the regression, linear fit of the obtained relationship, and by defining a suitable damage level depending on the selected engineering demand parameter, we could backfigure the values of the parameters such as eta and beta, which define the analytical expression of a log normal distribution of the probability of the relation, defining the relationship between selected intensity measure value corresponding to the engineering demand parameters relevant to a selected damage level, so that the conventional fragility curves. So first problem was to define the most suitable engineering demand parameters. Oh, sorry. And first for the structure, we selected the maximum interstory drift ratio, which represent the maximum tilt among the different load-bearing wall panels in the elevation as a representative engineering demand parameter for the out-of-plane damage mechanism. And the damage threshold were defined as the first one as the formation of tensile crack in the masonry at the toe of the wall. The following two damage levels were defined in terms of percentage of the ultimate limit state interstory drift ratio corresponding to the wall collapse due to overturning, which respectively correspond to activation of a rocking mechanism and the approach to a near collapse state due to overturning. For the foundation, we adopted nothing different than the typical performance parameter adopted for assessing the serviceability and and the failure limit state for the foundation building system, and in other words, the peak settlement and the tilt. Here you can see the plot of maximum interstory drift ratio against the peak ground acceleration relevant to compliant-based homogeneous soft soil models of clay brick masonry buildings versus the fixed base behavior. And it is clear that being the maximum interstory drift ratio higher for the soil foundation structure model, the both site and soil structure interaction effects prove to be detrimental for the structure. If we consider a heterogeneous soil model, which is characterized during the shaking by high values of induced shear strain and therefore higher energy dissipation, it somehow reduces the induced movement in the structure and therefore represents a less conservative evaluation of its performance. On the other hand, the homogeneous soft soil induces higher settlement in the foundations, especially for the more slender buildings characterized by more pronounced rocking motion and even of tilt values of the foundation. But whatever the case, even for the highest peak ground acceleration considered in our set of input motion, you can note that these parameters never attain the say threshold values assumed typically for the settlement and the tilt for the assessment of foundation foundation structure behavior for shallow foundations. So here in this slide, you can see the comparison of the log plots relating a maximum interstory drift ratio to different intensity measure, namely peak ground acceleration, peak ground velocity, and Hausner intensity, which is the integral of the spectral velocity in a wide range of structural periods. And you can see that for slender buildings on the right, whatever the intensity measure, there are higher difference between the soft soil building models, which are the red and blue and light blue dots, with respect to the fixed base model. This is due to resonance phenomena between, say, this building and soil dynamic behavior, whereas the difference are less significant for squat structures. And you can also check that for slender buildings, the interstory drift ratio is higher, as also shown before for homogeneous soil profiles. Here you can see an example of how we obtained the median of the fragility curves by simply intersecting the regression line with the damage level corresponding to each building model. And here you can see the comparison between the standard deviation of the scatter plots with respect to the best fit lines, which gives a measure of the say efficiency of every intensity measure considered, with the peak ground velocity and Hausner intensity measure. giving a lower dispersion, which seems to once more to indicate them as those most representative of the building damage with respect to the conventional peak ground acceleration. So in this slide, I want to resume a typical set of fragility function we obtained. In this case, these are the clay brick models of buildings. Here you can see the comparison between the fixed base fragility curve corresponding to squat and slender buildings, with this latter being, of course, more vulnerable with respect to the squat ones. Depending on the damage level, the difference are more and more significant. Where if we consider a homogeneous soft soil model, the curve are even higher, highlighting the detrimental effect of both side amplification and soil foundation structure interaction. And if we consider heterogeneous soil condition, instead we see as forward before a reduction at least of the vulnerability predicted for the structures. And if we consider the peak ground velocity instead of the Hausner intensity, in the second row, similar consideration apply for them. Then, as a final test of our procedure, we found out a significant case study where detailed observation of the damage was available, and it is the village of Onna, which was very intensely damaged by the L'Aquila earthquake in 2009. And for this earthquake, quite a reliable definition of the bedrock motion was available in the epicentral area. So we assumed that it was the same in the village of Onna. And from a literature paper, we found a detailed survey on the vulnerability classes of the building stock of the village, with the most significant part of buildings pertaining to the rubble stone masonry class we considered in our parametric study. We also could rely on a measurement of shear wave velocity profile obtained by surface wave methods, and therefore we could classify this soil type as kind of homogeneous sea soil among those we considered in our parametric analysis. So for the assessment of the damage distribution, we compared the observation with the prediction obtained by this set of fragility function defined for the three different intensity measures for the rubble stone masonry and soil type C we obtained from our parametric analysis. And here you can see the damage distribution for the vulnerability class we considered, but this damage was classified following a damage scale, which is that of the European macroseismic scale. So therefore, we first established equivalence criterion between our damage classification and that of the European seismic macroseismic scale, sorry. Here you can see in this histogram the comparison of the predicted damage distribution by using the fragility function expressed in terms of PGA, which is far from predicting the observed damage. Instead, if we use a peak ground velocity, here you can see the histogram relative to the fault normal and fault parallel components of the bedrock input motion, the agreement is more satisfying. But even more satisfying is the agreement observed by using a Hausner intensity as intensity measure for the ground motion. So we think that at the end, we can resume the result of this study with a few bullet points. First one, we effectively could extend the procedure for predicting elongation of fundamental period to to even complex geometries and mechanical models of unreinforced masonry buildings. This can be a method which can be a useful tool for evaluating the seismic load structure acting on structure by simply referring to capacity demand models and therefore response spectra derived from either seismic response analysis of subsoil classification or the assessment of the procedure on the measurement taken in the urban center of Matera was satisfying, but we cannot stop here. We would like to try to further assessment and extension of the method for irregular structural geometries. We started from very simple transversal two-dimensional model of soil and structure, of course, and we should account in some way for soil nonlinear behavior and energy dissipation. The fragility curve we developed can be helpful by simulation for simulating damage scenarios at territorial scale. If we can convolute shake maps, simulated shake maps through site and building classification databases, but we should assess this procedure against alternative approach, which are those most preferred by structural engineers, such as those expressing a probability of damage as a function of ground motion, including site amplification, but it must be said, neglecting soil structure interaction effects. Who knows which one works better? And finally, the consistency observed between the prediction and the observation in the Onal village is just the first step of assessment of the method, but we will wish to try further assessments on sites where on-site seismic record and detailed inventories of the damage mechanism can be available, if any. So to summarize, I can see that with reference to the oversimplified assumption of fixed base condition, we think that accounting for seismic response, which is trivial, and soil structure interaction, which is less trivial, can significantly improve the prediction, dynamic response, vulnerability of masonry buildings. Thank you very much. I'm sorry if I am being out of time. And
thank you. Thank you, Francesco, Professor. Do we have any question from the audience? Professor Pentilakis.
No, I know this work, so I have no. It is an ongoing work about the importance of site conditions and soil structure interaction when we are going to calculate and estimate the vulnerability of structures. Fixed structures present some deficiencies in this case, and the work nicely presented by Francesco lies exactly on this, how important is finally the soil structure interaction and site effects. If they are combined, probably they are even more important, but it is important to check one by one. And I think that this work is pretty much interesting. Thank you, Francesco.
Thank you, showing a very illustrated example for the detrimental effect of considering soil structure interaction, which usually people assume is safer for the period elongation. I'm curious about why the shorter period, shorter building is kind of less affected by this effect. As you show the aspect ratio, the shorter building is not much affected by this soil structure interaction.
In which case do you mean? You mean that of the test site of the, yeah.
The first case, you have a shorter square building. Yeah, that one is not much affected by this, considering soil structure interaction.
Actually, in this particular set of 4 buildings, we understood that the thickness of the clay layer is relatively low and is increasing from one building to the other, but not as significantly as it would be required to significantly modify the resonant frequency. Broadly speaking, anyway, the squat buildings are less significantly characterized by rocking motions. And the parametric study also showed that the slender buildings are characterized by, for instance, a higher variation of the period and higher fragility with respect to the squat buildings on same subsoil conditions, and therefore this should be attributable to, say, kind of two mechanisms. One is the rocking occurring in the slender buildings, and the other one, which increases the interstory drift ratio. And the other one can be some kind of resonance, at least in our particular models, we observed that for the slender buildings on soft soil, there was also a resonance effect. So in this case, is a combination of both site amplification and soil structure interaction, which is detrimental. So I agree with Kyriasis. We have the numbers, say the results to separately analyze the different effects. And so one of the first steps should be that of, for instance, considering what is obtained by uncoupling the soil free field response from that of the structure, instead of considering them as well. But we have anyway included in our model the fixed base conditions. So we have already the data which characterize the fixed base behavior of the building, and therefore we just need to combine them with the results obtained in terms of free field ground motion, accounting only for the amplification.
May I make a more general comment as well, which in my opinion may influence all the results that you have presented. We are working as well, as you know, on this. It is the actual bearing capacity of the foundation compared to the admissible loads. I believe that this is also a parameter which may affect considerably all these results. Because a lot of structures, masonry structures, are built with not accurate bearing capacity estimation, either because of the lack of knowledge of the soil conditions or the way that the builders would see the foundation system. I believe that this is also something that we should investigate, the importance and the parameters involved with the real foundation system that we have, comparing the actual bearing capacity and the admissible loads. It's something quite important, especially if you are introducing the rocking effects and all these kind of things. It's equally important.
Yeah, sure. I believe that this is a crucial point as well. In our analysis, we checked that although attaining a significant plastic strain distributed in the foundation soil, kind of a global failure mechanism were never attained. Anyway, I showed that even in the worst case, the say displacement and tilt of the foundation were not as worrying. But anyway, the problem exists because, first of all, this was a check that for us pointed out that the assessment of safety for this kind of models had to be done in terms of structural damage, not foundation damage, and therefore the strength hierarchy in our models was more or less, say, the conventional one,
Yes.
with the structure damaging before then the foundation and the soil, and not that, say, for instance, defined by George Gazzetas with the inverse hierarchy of strength, and which can happen maybe for some kind of a particular structural models, but not in this case, I believe. And of course, it also depends on how you define the foundation geometry and that and so on. So we will try on further models also to turn upside down the structure and soil strength hierarchy to see what happens possibly.
All right, thank you very much. I think we need to wrap up the day. It's 6:30 Beijing time. So
Yeah.
Thanks again for the two speakers and all the speakers today. So let's give the floor to the organizers.
Thank you very much, both Julia and Francesco. Thank you.
Thank you, Professor
Thank you, chairs.
Viviani. Thank you, Professor Silvestri.
Thank
And
you, Louis.
Thank you, Professor Petelakis and Professor Wang for chairing this session. So I